In the previous segment, we introduced different types of energy, and we talked about how within a system, energy can be transformed from one form into another form. Now, we can add energy to a system or remove energy from a system. Recall that the system is our collection of interacting objects, and the environment is the rest of the universe. So we can add energy to the system. For example, let's say that my system is the ball and the box. That's my system. How much energy? I don't know. We'd have to know some numbers to calculate it, but there's some potential energy here, right? The ball's not moving, so there's no kinetic energy. How about now? Oh, didn't I give the ball some kinetic energy? So I am not part of the system. In this experiment, I am part of the environment. Did I not add some energy to the system, right? No kinetic energy, kinetic energy. Great. So I added some energy to the system. How did I do that? I pushed on the ball. So that's one way that we can add energy to a system. I can do work on the system. And work is the mechanical transfer of energy into or out of a system via pushes or pulls. And of course, what are pushes and pulls? They are forces. So a force can move energy into or out of a system. Now, work is not the only way to add energy to the system. I could get my lighter here, and I could hold it next to the baseball for not too long. And I would increase the temperature of the baseball. So I added thermal energy to the baseball. Well, I didn't do that by pushes or pulls, did I? So that wasn't work that I just did. Instead, I added heat to the system. So heat is the flow of thermal energy. We want to be careful. We'll talk more about this in chapter 11. But things don't have heat, right? I added some heat to the ball. That gave it thermal energy. So we just need to watch our language. And we'll talk more about heat in chapter 11. So these two things, work and heat, they change the energy of the system. They're called transfer variables because they transfer energy into or out of the system. And so work and heat define how, energetically, how the system interacts with the environment. And just like something doesn't have heat, the ball does not have work. I can do work on it and give it some potential energy. So it can have potential energy. It does not have work. Why? Because these are transfer variables. It's how we move energy into or out of the system. They are not properties of the system itself. So here are some examples of some energy transfers by work. Here, this athlete is doing work on the shot put in order to give it some kinetic energy. So if the system is the shot put, then this gentleman is increasing the energy of the system by doing work on it. Here, if my system is the match and the surface that it is next to, then by doing work on it, by applying a force to that match, I am increasing its thermal energy, causing it to be hot enough that that orange stuff on the end of the match spontaneously ignites. In this picture here, we see a kid with a slingshot, and this kid is doing work to add energy to the slingshot rock system, right? So if our system there is the slingshot and the rock, then he is doing work to increase energy of the slingshot rock. What kind of energy? Spring potential energy, because this position has less energy than that position. It is potential energy or energy of position that work is creating. Okay, so that's work. The work energy equation, this makes it sound like it's some big old deal. It's kind of not. All this says is just this is the mathematical version of what I just said. If we're going to change the energy of a system, we got to do some work on it. And again, in this case, we are neglecting heat, right? So we're going to push heat off. Now that we've introduced what it is, we're going to kick it down the road. We're going to push it to chapter 11 because it deserves an entire chapter to itself. Okay, so we're going to kick heat down the road, talk about it in the next chapter. For right now, then, the only way we're going to move energy into or out of the system is by work. And so if I do some work on a system, it will change the energy of the system. That's what this equation says, right? So not too bad. Hopefully I already convinced you of that. This is just the mathematical version of that statement. What kinds of energy might I have created within the system? Oh, I can create any kind I want. I can create some kinetic energy, some gravitational potential, some spring potential, some thermal energy. Heck, I can even create chemical energy. With a generator, I can do work and create electrical energy. All kinds of stuff. Again, how do I change the energy of a system? I do work on it. So this brings us to the law of conservation of energy, which, like I said in the previous segment, is possibly my favorite idea in all of physics. The law of conservation of energy says the total energy of an isolated system remains constant. Most students have run across this idea previously in their education. And maybe you heard a slightly different statement of it. Maybe you heard energy can never be created or destroyed. I think I like that, right? That's a great definition. A lot of times this shows up mathematically as being the initial energy equals the final energy. That's also a great way of visualizing it, of wrapping our brains around it. But the point is that the total energy of any system remains constant if we account for all of the different forms. And it's such a surprising thing, right? I mean, I started out this chapter by saying energy. It's hard to define, right? It's this mysterious quantity that for some reason remains constant in all sorts of different processes. And this is an interesting idea. It kind of comes out of Newton's laws, but it wasn't really until the 1700s and the 1800s that scientists really worked out all the details of this and became completely convinced of its validity. So what does this mean? Practically, what does the law of conservation of energy mean? Well, okay, so cool ideas. What does it mean? Well, let's go back to this ball on my box, right? So there we go. There's that ball. It's got some energy because it's on the box. What kind? Potential energy. Conservation of energy says that this potential energy didn't just show up from nowhere, right? It means that it existed in a different form previously. Okay, so let's rewind. The ball was down here. Before I put it up here, it was down here. How did it get its potential energy? Well, I lifted it up. So didn't I do work on it, right? So I did work on the ball in order to put it here and give it some potential energy. How did I get the energy in order to do work on it? It came from my breakfast. I had oatmeal and eggs for breakfast. So my oatmeal and my eggs right now are currently being digested, and my body is converting that chemical energy that is stored in my oatmeal. It's converting that into, well, the kinds of energy that I output, right? So right now I'm converting chemical energy into heat, certainly some thermal energy, right? But I'm also converting chemical energy into potential energy of the baseball. So the potential energy that the baseball has right now, only a few moments ago, was chemical energy stored in my body. And a few hours ago, it was chemical energy stored in my oatmeal. Did it just show up in my oatmeal? Where'd the energy come from there? When I ask students this on an exam, I often get the answer, you microwaved it, so that's where the energy came from. My oatmeal gives me exactly the same amount of energy to do things and go about my day, if it's hot or if it's cold. Right? The energy that I absorb from my oatmeal is not because it was warm, right? I get exactly the same number of calories from my oatmeal, whether it's cold or whether it's warm. How did the calories get in the oatmeal? They got in the oatmeal because the oats grew in a field and they absorbed energy from the sun, which is just so cool. Chlorophyll is this amazing, amazing molecule, and it captures sunlight energy and turns it into stored chemical energy in the form of glucose. It's such an amazing thing, right? It's so amazing. Plants store sunlight energy in the form of chemical energy, and I eat it and I use it to lift a baseball. That's pretty cool. So that means that the potential energy that this ball has right now was a few moments ago, chemical energy in my body, a few hours ago, chemical energy in my oatmeal, a few months ago, probably really last summer, so maybe a year ago, it was light streaming through space. From where? From the sun. So that energy was light energy in the sun. Where did that come from? Well, in the core of the sun, 4 hydrogen atoms get smashed together to form one helium atom. Guess what? That one helium atom has a tiny bit less mass than those 4 hydrogen atoms put together. What happened to that mass? It became energy. That's pretty cool. Possibly the most famous equation in all of physics, possibly the only physics equation you knew before you came into this class, was E equals mc squared. What does this equation mean? Well, E is energy, m is mass, and c is the speed of light, which is a really big number. What happens when you square a big number? You get a really freaking big number, right? So c squared is an enormous number. It is the speed of light squared. It is huge, which means that a tiny bit of mass can be transformed into a huge amount of energy. We're going to save a complete discussion of this equation until the end of next semester. So we'll kick that down the road a bit. But back to the oatmeal and the baseball on the box. Last summer, the potential energy that this baseball has it was in the form of sunlight streaming through space. Before that, that energy was in the sun, and it was in the form of mass. It was in the form of hydrogen atoms that you could literally hold in your hand. That is so crazy, right? This is such an abstract form of energy, this potential energy. Mass is concrete, it's physical. That's crazy. Okay, so that's how this ball got some potential energy. You know, I could knock it off. I could knock the ball off the box, is what I meant. I knocked the ball off the box. What happened to that potential energy? Well, for a minute it was kinetic energy. For a brief second, I should say, it was kinetic energy. As the ball fell, we saw potential energy converted to kinetic energy. But now, you can't see it, but the ball is at rest on my desk down here. So that potential energy is gone. The kinetic energy that was briefly created is gone. Did it disappear? It did not disappear. Conservation of energy tells us it did not disappear. It is still somewhere. What form? Thermal energy. This basement that I am in is a tiny bit warmer because I dropped that ball. So we see this transition from mass, a highly ordered form of energy, to thermal energy, a very disordered form of energy. And this is what's happening throughout the universe. This is what humans do. This is just a process that's happening. The energy remains constant. The disorder of that energy increases. And that's touching on an idea called entropy, which we will also revisit in the next chapter. Entropy is a measure of the disorder of the energy. To put it in another way, entropy is a measure of how useful energy is. To put it another way, entropy tells us how easily a form of energy can be transformed into another form and therefore used, right? So large amounts of entropy are large amounts of disorder. So that energy that is now thermal energy dissipated throughout this room has a high amount of entropy. This highly organized mass in the sun, that this energy, that was the form that this energy was in not that long ago, that is a very low entropy state. But the total amount of energy remained the same through that whole process. Pretty cool idea. So if we were to write an equation for the conservation of energy, again, without including heat, because it's such a big topic and we're kicking that down the road to chapter 11, right? So neglecting heat transfers of energy by heat. If we were to write an equation for the conservation of energy, it ends up looking like this. And again, energy is not a vector, so there's no directions to worry about here. A few things to note. This work other, it can be either positive or negative. So we can either add energy to the system or take energy out of the system with work. And again, for now, we're ignoring heat. And thermal energy is special. We'll talk a bit more about that. When energy changes into thermal energy, this change is irreversible. And so that's kind of what I was talking about a minute ago with this transformation from mass in the sun to thermal energy in this room. There's no way we can go back, right? Now that that baseball has dissipated its energy as thermal energy in this room, there's no way that we can recreate mass out of that. Okay, so this is about as far as we can get with this right now without defining all of these different variables. We have equations for these different things. So we're going to stop conservation of energy for right now, and we're going to revisit it after another segment where we introduce the equations for each of those terms.